I'm going to be talking about the High Frequency Active Auroral Research Program, which is in interior Alaska. And this is pretty current. It's for 2020. So let me make sure I can scroll. I'll just talk a little bit about me. I don't want to concentrate too much on that. And then I'm going to go into the HAARP Science Facility and then go on to a photo tour. And with only a couple exceptions, these are all pictures that I've taken since about 2016 or 2017, when I made some tours of the facility. And so we'll just go on a photo tour. And then I'm going to talk a little bit about the projects that I am specifically working on. These are non-HAARP projects, but I've built an observatory within an observatory at HAARP, and I have some space weather and Jupiter radio projects going up there. And then I've also got some web links and references for you. And if you want to have a copy of this presentation, I can send you a PDF file. So my contact information will be at the end, and I think Harry also has it. So you can get a hold of me and I'll send you a copy of this presentation. So as far as me, I've lived, educated, worked in Alaska all my life. I was born here. In fact, I was born in a hospital. It's only a couple miles from where I live right now. And I worked in the airline and telecommunications industry as an engineer. Owned and operated an engineering firm for 35 plus years. I retired the company in 2009. And now what I do is manufacture instrumentation for radio astronomy. And it's low volume type stuff. Everything is hand built and ship it all over the world, just about every country on the planet. And I've built 3 amateur radio astronomy observatories in Alaska. The first one in Anchorage, which is where I am right now and where I live. And another one at a small town called Coho, which is southwest of Anchorage, maybe as the crow flies, maybe 80 to 100 miles or so. That was in 2015. And then in 2019, I got permission to build an observatory up at the HAARP facility, and that's remotely operated, as is Coho. And what I'm doing is mostly solar radio in the HF and UHF bands. I operate 3 E-Callisto solar radio spectrometers, one at each of the observatories, and that's an international project. Space weather type project. And I also operate long wavelength array antennas and accessories. And I'll go into that a little bit more later. Jupiter radio in the HF band, this is in nominal 20 megahertz. Jupiter as a planet is the second most powerful radio emitter in the solar system next to the sun. It's got a huge magnetic field, and so it is able to put out a lot of power. And so what I'm trying to do is a little bit of radio science from an amateur point of view, and I'm mostly interested in the radio propagation aspects of these types of observations that I make. Solar flare effects on VLF and LF radio, solar flare effects on HF propagation, and so forth. I also am actively involved in meteor trail reflections at HF. And I use, unlike most people who use VHF, for example, FM broadcast stations for meteor trail reflections, I use WWV and WWVH. So I'm operating in the HF band at 15, 20, and 25 megahertz. Also operate a geomagnetometer using the SAM3, which is another project that I've been working on for about 10 years, and I actually sell the magnetometer kits. So here's where I am. I assume you can see my mouse. I'm in Anchorage here, and the HAARP facility is up here. And I can drive to it. It takes about 3 hours and 45 minutes to drive up there through the mountains. And my other observatory in Coho is down southwest of Anchorage down here. And I know that there's a lot of people that think that Alaska is part of Canada, but the last time I checked, it's actually part of the United States. Now, the HAARP had open houses in 2016, 2017, and 2018. And those open houses were initiated by the University of Alaska in Fairbanks, the Geophysical Institute, which now owns the facility. They acquired it from the Air Force in 2015, and so it's now a private, non-government owned and operated facility. I wrote several articles about the HAARP. They were published in the Journal of the Society of Amateur Radio Astronomers, SARA. And through those articles, I was invited in 2019 for a personal tour. Now, I'd already taken self-tours of the facility, but this one I got to see virtually every instrument that's on that site, and it's a huge site. There's 8 science stations. The biggest one is the ionospheric heater, the ionospheric research instrument, IRI, which is a huge transmitter. And I also spotted a TCI 540 HF antenna that was way back in the woods and wasn't being used for anything. So I kind of jumped on that. And this is a picture or a line drawing of that antenna. And these towers here, each are 100 feet high, 30 some meters. And so it's a pretty good sized antenna. It's a horizontally polarized HF antenna. And I asked the owners, the Geophysical Institute, hey, I'd like to connect to that thing. And they said, send us a proposal, which I did. And almost immediately, I got permission and hooked up a bunch of different receivers to it during the summer of 2019. The Callisto, which is a solar radio spectrometer with an up converter, and I monitor 4 to 40 megahertz with that. I have an RF Space Cloud IQ SDR up there, which anybody can access. It's set up for open access right now. And I also installed an HF or an AirSpy HF Plus software-defined radio receiver on the same antenna. And so those are what I got connected up there to that antenna. And then in the fall of 2019, I installed a Radio Jove receiver and a dual dipole antenna for Jupiter radio observations. And that operates at a nominal 20.1 megahertz. I updated that proposal to the HAARP people to install a long wavelength array, or LWA antenna, and which it's an active cross dipole that operates from 5 to 105 megahertz. And I got part of the installation done just before winter hit. And so I haven't been able to complete that yet, but I hope to, as soon as it warms up a little bit up there, I'll make a trip and finish that installation. That'll include a couple Callisto instruments. These will operate over the full frequency range. And I use my own power coupler to power the active, the amplifier in the antenna itself. And then I also have a quadrature coupler in there so that I can derive circular polarization from the cross dipoles. And that's important because a lot of the emissions from the sun are circularly polarized. So they're kind of fun to capture. Okay, so what about HAARP? The whole idea originally was to be able to modify a certain small patch of the ionosphere and make it do things like emit VLF emissions, also alter UHF satellite transmissions that pass through this patch. So it actually does heat the ionosphere, adds energy to the electrons and the ions in the ionosphere from about 100 to up to 350 kilometers. So that covers in the E and F regions of the ionosphere. And so that's this illustration that you see here is pretty well summarizes everything that's going on. You have your HAARP transmitter down here, which is altering the ionosphere directly above it, and the magnetic field lines are in there as well. And so the whole thing works together then to alter radio propagation either into or through that part of the ionosphere. It's not affecting anything else. It's not causing earthquakes in Afghanistan. It's not altering anybody's brain waves that I know of. It's not doing any of that monkey business. So it's strictly a science facility. Here's another illustration that I took from one of the documents associated with HAARP. And here's the transmitter down here. And you can see that there's a lot of stuff going on up here. And the geomagnetic field is pretty steep. The lines have an angle of about 76 degrees with respect to the horizon. So they're pretty steep, and they have play a large part in how radio propagates through the ionosphere. So you can see that there is some activity in the D region, which is the lower region, the E, and the F. And the F region is where a lot of the action is when they're doing their research campaigns. And you can see that there's a lot of stuff that goes on here, ELF and VLF emissions from this activity are received by receivers on the surface. We have scintillation receivers that detect transmissions from satellites that are above the ionosphere, and the radio waves pass through and are scintillated as they pass through this region that is being modified by the HAARP transmitters. So there's a lot of stuff going on there, and it takes a lot of horsepower to do that. And I'll be talking about that a little bit more. The facility construction started in 1993. But it didn't actually go into operation until late 1994. It was owned by the United States Air Force, originally set up to be an over-the-horizon radar. Now, it was totally a political thing back in the 90s, but then somebody wised up and decided to change it to a science facility. And all of us taxpayers sunk $290 million into that facility. So, and it operated for almost 20 years by the Air Force. And when they were operating that thing, they ran it 24 hours a day, 7 days a week, 30 days a month, 12 months a year. That thing was operated almost continuously for about 20 years. They finished their mission in 2013 and immediately went in, sent some contractors in with hatchets and started chopping up the place, but they didn't do enough damage so that it couldn't be fixed by the Geophysical Institute, which acquired the facility, for, I think, for $1 in 2015. The UAF GI had several research campaigns from that time through 2019. And then when the COVID-19 pandemic started really getting active, there virtually is nothing, there's been no research done at all in 2020. And we're not anticipating anything going on until next year sometime. So here's a Google Earth view of the facility. And this line down here on the lower left-hand corner is about 1 kilometer. So that's 6/10 of a mile. And just to give you some a sense of distance, from the main operations building over here, which is near the main highway or the highway that drives by there, it's about a mile from that point up to this science station up here. And this is where I have my stuff located. And that TCI 540 antenna that I mentioned a few minutes ago is located right here. So it's about a mile in. And this square that you see right here is the ionospheric research instrument. That's the huge transmitter array. And I'll show you some more pictures of that in a minute. But you can see there's science stations and science pads all along these access roads. And there's all kinds of stuff. There's magnetometers, there's optical telescopes, all-sky cameras, rheometers, receivers, spectrum monitors, all kinds of stuff going on up there. Now, not all of that is in operation. Some of those instruments have been shut down, but there's still a lot going on. Now, the IRI, its purpose is to add energy to the ionosphere above the facility. And these transmissions are made near the plasma frequency of the ionosphere or harmonics of that frequency. And so it operates down to a minimum of 2.7 megahertz and a maximum of 10 megahertz. So it's really not a really, really wide range transmitter, but it does cover a significant part of the HF spectrum. Now, the IRI is only part of the story. The rest of the story is the diagnostic instruments that are on site or off site. And these are to observe and record the effects on the ionosphere of the transmissions by the IRI. And these can occur ELF through the UHF band. So as low as 3 hertz or a few hertz, all the way up to 3 gigahertz or so. So just by adding energy to the ionosphere in the HF range, we can induce emissions over quite a wide range. And when I say we, I mean the people that operate the facility. Now, when you're working with the ionosphere, there's 3 important frequencies, and these are involved in radio propagation. You probably already know this. There's the plasma frequency that depends on the electron density in the ionosphere. There's the gyro frequency, which depends on the magnetic field vector, direction and flux density, and then you have a collision frequency between ions and electrons and atoms and molecules. And that's a rate of collision that can affect the radio propagation. So when you're operating the HAARP facility, that's what you're trying to do, is you're altering or seeing the effects on these 3 different frequencies that are characteristic of the ionosphere. Now here's a ground photo of the IRI, and you can see that there are a lot of cross dipoles. So this distance from the ground down here up to about here is approximately 72 feet. So that'll give you a sense of what we've got going here. And there are two dipoles crossed on each of these towers. And I'll show you some more pictures. I'm going to give you a, let's see if I can figure out how to do this. I want to show you a movie that I've got on my PC here. So I'm going to stop share for a second, get that movie going. And so let's see.
If it has sound, make sure you enable share computer sound in the lower left-hand corner.
Yeah, I'm not on mute right now. You should be able to hear me.
Yes.
Yeah, okay. I'm just trying to figure out how I'm going to get to this movie.
Is it on your computer or on the web?
It's on my computer, and
then you have to find it, open it.
Yeah, I've done that, and so now I'm going to go back to share my screen.
Right, choose that
and show you the movie, and I'll fumble through this again once it's done. So you should be able to see a winter scene there now.
Beautiful.
Okay, so this is a drone view of the facility that was taken in November of a couple years ago. So it's a winter scene, and we're going to take off from one of the corners and fly over the antennas. And you can see these are the dipole antennas. These white buildings that you're seeing scattered around are the transmitter enclosures. And then these boxes here are high voltage transformers. The power is distributed at 12,470 volts, and then step down to 480 for the transmitters. So I'll play that one more time. It takes a minute for that thing to get off the ground.
The transmitters are linked together and are synchronized, or they're on different frequencies?
Yeah, the transmitters are all synchronized. They all operate exactly in lockstep with each other. I'll give you some statistics on this as soon as this is done. Okay, so now let me get back to, okay, we should be seeing the presentation back on the screen. Is everybody seeing that okay?
No, we're still seeing your, you have to do a new share or end and start.
Oh yeah, okay, you're right. Sorry about that. Let's see.
But from the view options, you can do new share at the top of the screen. Yep.
Okay, are you seeing it now?
Yeah, perfect.
Okay, excellent. Okay, so let me talk a little bit about the IRI. There's 180 antenna assemblies that we just flew over, and each of those assemblies consists of 2 dipoles in a cross configuration. That gives us a total of 360 dipoles. And that facility, or that area that we just flew over, is over 1 million square feet, 30+ acres of real estate. So it's a huge, huge operation. And here's a line drawing of those dipoles. And these are really interesting dipoles. The drawing on the left here is a composite. This is the whole thing that you saw from the ground and from the air. And it actually consists of 2, in each dipole consists of 2 independent antennas, a low band dipole at the top, which you see here, and then a high band dipole below it that you see here. And not shown in these drawings, there's actually a ground screen that's about, I don't know, maybe 5 meters above ground level that covers the entire area. That full 30 acres has got an elevated ground screen. The array is directional. It can be steered 30 degrees from vertical, and it can be steered pretty doggone fast, 15 degrees in 15 microseconds. The main lobe beam width varies with frequency, as you would expect. About 15 degrees at 3 megahertz up to about 5 degrees at 10 megahertz. And the directivity, approximately the gain, varies from 20 to 30 dB depending on the frequency. So that's the main lobe when everything is focused together. And if you, I hope you can see the detail shown in this image here. This is a photograph. You can see the ground screen. It's above me when I took this picture here. And it's just a cobweb of both conductive and non-conductive guy wires, messenger strands, and so on that support the antennas and also make up the ground screen. There are antenna matching units that are mounted up on the tower, and these actually are tunable components. There's inductors inside these cans, so there's one for each of the low band and high band dipoles. So you have 4 total for 2 cross dipoles. And this is a detail of how all that stuff is mechanically tied together. Some of these strands that you see here are conductive, some are non-conductive. They're either structural or functional and electrofunctional. So there's just thousands of these things in the air above those antennas. 160 transmitters, each transmitter is 10 kW, and that gives you a total of about 3.6 megawatt total power. And it's these transmitters with the antennas are automatically and continuously tuned to the selected frequency. So when you switch frequencies, it happens instantaneously. And this is something that a lot of people don't realize, is that the HAARP facility is always operated, has an operating authority under the FCC. Its service code is the experimental research and experimental test. And they operate under special temporary authorizations, STAs, with a call sign WI2XFX. So they got a legitimate call sign. They operate under the FCC. They can put out an effective radiated power as high as 2.8 gigawatts up into the ionosphere. And as you would expect, and as you would hope, certain frequencies are notched out to prevent interference. So when they're sweeping the transmitters, they actually notch out specific radio or specific frequencies in some of the radio services. Now, I'm not sure about the ham bands when they go through the lower ham band, if they're notching those out or not. I kind of suspect they're not, because I think, well, I don't know why, to tell you the truth. There's the transmitter enclosures. There's 30 of those. And they look like a shipping container, because that's what they originally were. There's 30 of those, and here's a view of the inside of one of them. And there's a middle aisle, and on both sides of the aisle are the transmitter cabinets. And one of the cabinets over here on the left, on the right, has been opened up, and you can see some of the tuning elements. These are actually variable inductors that you're looking at there. And this is another view. Here's the transmitter tubes, and these are chimneys for forced air cooling of the tubes. And like I said earlier, these are 10 kW power amplifiers. And here's a coax connection to one of them here. And I believe it's 1 5/8 inch heliax that they're using for this. I haven't actually seen the inside of a piece of this cable, so I'm guessing on that. But you can see that it's pretty good sized stuff, and it has to be to carry the power that that they operate at. And they don't operate at a perfect one-to-one VSWR. So the reflected power and all that will heat up those coaxes, and that's why they're so big. Here's one of the transmitter tubes. I don't know the number of that guy, but they are not something you can go and buy at Radio Shack or buy through Mauser or DigiKey. They are fairly hard to get. And in fact, the Air Force, when they shut down the facility in 2013, they removed all the tubes from the transmitters, but they were able to recover every one of them. And so they didn't actually lose any tubes that I know of. Here's the operations center and the power plant. And you can see, get a sense of scale. Here's some cars that are parked out in front of the facility. And this tall structure here was originally for the over the horizon radar that was envisioned for this at the very beginning. And it's unused now. There's nothing up there except maybe some storage space. Over here on the right, you can see 5 stacks, and those are for the generators that power the facility. Now, when they fire up these transmitters, they disconnect the electric utility in the area. It's a rural electric co-op. They disconnect them and then switch over to these generators. And when they're operating full power, there's a continuous stream of diesel fuel trucks that are coming into and out of that site to feed those generators. Here's a picture of the generators themselves. They're 4,000 horsepower diesels that were originally in Navy tugs. So surprisingly, the Navy actually gave something to the Air Force. I don't know why, but they did in this case. And each one of those generators, or each one of those engines, is coupled to a 2.6 megawatt generator. And there's 5 of them total. And they only use these diesels during research campaigns. Otherwise, they operate from the rural electric utility. This image is the control center. This is where all the stuff's going on. Even though they have local control of everything, it's possible for someone remotely to program the sequence of transmissions and so on, so that you don't have to necessarily be at the site in order to do your research campaign, in order to actually control the transmitters. Now, there definitely are going to be people there that are going to keep everything running, keep the diesels running, make sure the transmitters are working properly and all that kind of stuff. But for an individual researcher, he doesn't have to be there when this thing is in operation. Now, the diagnostic instruments are the other half of this story. What they're trying to do with these instruments is to identify and characterize the physical processes that are going on in the ionosphere. And there's at one time, there was a very, very large suite of instruments to measure these effects. Some of them have been decommissioned, they're no longer needed or no longer used. They had magnetometers. In fact, there still are magnetometers on site, both induction and flux gate type magnetometers. There's a digital ionosonde called a digisonde that operates 24 hours a day, year-round at the site. And in fact, the data from that device is publicly available. If you're interested in the ionosphere directly above the HAARP facility, you can definitely get that information. Now, this digisonde is important during research campaigns because it's what's helping them determine how to manage the frequencies that they're transmitting by the big transmitter. Here's a picture of the digisonde. It's not all that impressive, maybe 24 inches high or 30 inches high. So it's just a small rack-mounted transmitter and receiver, and it's pretty well self-contained. You can cut the power to it, turn it back on, and it'll reboot and start up and go back into operation. It's all pre-programmed. You can see a CD drive up here. There's hard drives in it. So it's a completely self-contained ionosonde. Here's the receiver antennas, digisonde receiver antennas. They're crossed loop antennas. And there's actually 4 of them. You can see one in the foreground here, and then one in the background. And then there's back behind the trees here, there are a couple more, and they're actually in a triangular shape with one of the antennas in the middle. And this one that you see in the background is the middle of the 4 receiver antennas. Now, those are located about maybe 100 meters or so from the transmitter antenna. And this is an inverted V, a crossed inverted V antenna. You can only see 2 of the towers associated with it here. There's actually 2 towers off to the sides that aren't in the picture here. So this is one of the diagnostic instruments that's critical to the operation of that facility. There's also radiometers that operate down at the VLF and ELF frequency ranges. And these are important for doing research having to do with polar cap absorption, radio noise background measurements, and so on. There's a VLF D-region remote sensing receiver. It's actually off-site, but in Alaska. Imaging rheometer, that's just a device that measures the radio noise from the cosmic radio background. And if that noise increases or decreases, then you know there's something going on in the ionosphere. And it's you're able to make some determinations from that. The ELF and VLF receivers, there's some off-site in Alaska. There's one set up in Greenland that's associated with HAARP. There was a modular incoherent radar system at this, well, there still is. It's physically still there, but it's been decommissioned for several years now and is no longer being used. But it operated in the UHF range, 449 megahertz. And I know of several researchers who got their PhDs using that instrument. There's a scintillation monitor that is used to monitor satellite transmissions. And so there's scintillation whenever you alter the ionosphere above HAARP. And this is a receiver antenna here that's used for that purpose. There's also another off-site radar, the SuperDARN, and that stands for Super Dual Auroral Radar Network. And this is a part of the SuperDARN radar is part of a radar network that's pretty much scattered all around Canada and the US. And there may be even some in Europe as far as I know, but I mean, I don't know for sure, but the SuperDARN is another facility that is used to monitor the ionosphere above the HAARP facility whenever they're doing anything. There's optical telescopes up there for observing what is called air glow, artificial aurora. In other words, northern lights that are produced by the HAARP transmitter. Here's an optical imager that's at the facility at HAARP. And some of these, there's actually quite a few of different optical instruments, some that are still in operation and some that have been decommissioned that were decommissioned by the Air Force and haven't been resurrected. There's other things at the HAARP facility too. There's an aircraft radar and a traffic collision avoidance system, TCAS, aircraft detection type radar system. And these things are set up so that if any airplane comes within the HAARP beam or comes near the HAARP beam when it's in operation, it will automatically shut down the transmissions so they won't burn up anybody's airplane as they're flying over. So those, that's pretty much, here's a picture of the radar. Here's the radar. Here's a TCAS and GPS antenna here in the enclosure for it. So these are at the HAARP, and that's pretty much what we've got for diagnostics. There are some non-HAARP experiments going on up there. Here's a rheometer antenna, and you look at that and you say, wow, that doesn't look very good. But it works. And this particular one is for a reason that I haven't been able to determine. It's part of a network that several Japanese researchers have built in northern areas. And so they're doing some studies of the cosmic background radiation with these antennas. And you can see that it's kind of swampy. Here, this is all water, and it looks like a raft. Their instrumentation's floating on it. And this was taken in, I think in April of 2019. Okay, so how about research? I mentioned earlier that there are several campaigns in 2017, 2018, and 2019, but none in 2020 due to the COVID-19 pandemic. I understand that they're working on having one maybe in March of 2021. That's a possibility. But some of the things that they've been doing since the Geophysical Institute took over is they had a campaign in 2017 where they used the HAARP transmitter to demonstrate the so-called Luxembourg effect. And this was kind of a citizen science crowd-funded experiment. I don't know if any of you had ever heard of this, but there was an individual, and maybe I have his, no, I don't have his call sign, but he actually did some crowdfunding and was able to buy about an hour of the transmitter time. And they charged a nominal $5,000 an hour for the transmitter. Now, don't for 1 microsecond think that that actually covers the cost. They do that just to make it attractive for one thing, and then hopefully more people will be using it, and then they can start getting an actual recoup their investment in, or recoup this taxpayer's investment in it. There was another campaign in 2018, maybe some of you heard about this, and that was using the WHISPER protocol, where they transmitted that protocol and then saw how what they did is they transmitted in certain directions with respect to the magnetic field, so that they could study how the propagation changed depending on how the beam of the transmitter was oriented with respect to the magnetic field. And Dr. Chris Fallon, who was the chief HAARP scientist at the time, is the one that did this. And he wrote some articles about it. I think there was an article in the QSD magazine about it, a short article. Another one in 2019 involves citizen science, and that was to transmit images in the ionosphere for an art project. This was actually funded by the Arts Council in Canada, and it wasn't cheap. I mean, we're talking big dollars here. And a lady came up from Canada and specified what she wanted to do, and that was to transmit images using slow scan TV into the ionosphere and somehow make an art project out of this. I never really fully understood the full story on that, but it was definitely a big success for her. And it also was a success for other researchers because they could set up their diagnostic instruments to make measurements, and there was, as far as they were concerned, it was just another transmission. So this really paid off, I think, for everybody involved in it. It was kind of fun, I thought, but unusual for a science project. Okay, now what about the stuff that I've got at HAARP? Well, I've got, I installed a bunch of electronics up there in 2019. They set up a heated and cooled enclosure for my exclusive use. And so here's one of the cabinets that I installed. And this has got some power supplies and some splitters. This is where the Callisto instrument is located inside this guy. And so it's just a small, I don't know, what's that, 12 3/4 inch high, or maybe 15 inches high. So there's just one cabinet shown there with the electronics in it. You can see a Cloud IQ software-defined radio receiver down here. And then over here on the right-hand side, just barely visible, is an AirSpy HF Plus receiver. And so that pretty much shows a picture of most of my electronics. There's also a computer associated with it. I have a UPS, and here's my router, my gateway and router for the internet access that I have. And you can see thermostats for heating and cooling in the background here. So that's pretty much my instrumentation. Here's a block diagram of what I'm doing. And you can see the TCI 540 antenna. That's that big antenna that I showed very early in this presentation, is over here on the left-hand side. I had a preamp out there to compensate for the long cable that comes back to my enclosure. I have about 800 and some feet of RG213. that I installed up there, and that RG213 was salvaged from a imaging rheometer at Fairbanks that was decommissioned, and I got about 1,200 feet of cable out of that for nothing. So I used 800 plus feet to come back to my enclosure, where I've got a bias T for powering the preamp, power supplies, various voltages. I have a wideband splitter that I split out. This is an HF antenna, so I'm splitting out in the HF band to the Callisto instrument with an up converter, the Cloud IQ. The AirSpy is also connected to the splitter. And it all goes into a computer, and the data is uploaded from Callisto, is uploaded to a network in Switzerland, where all of the Callisto receivers around the world, I think there's maybe a couple hundred of them around the world, where they provide data into the server. Now down here at the very bottom, you can see a dual dipole and a Radio Jove receiver. This is a fixed tune receiver that it's tuned to 20.1 megahertz, and its sole job is to listen to Jupiter radio emissions. Now, Jupiter for the last couple of years has been fairly quiet, especially the last year. And it's because of its physical position with respect to the Earth in orbit. And so I've been using it for solar radio type stuff as well. And this dual dipole gives us a little bit of gain to the south. And so whenever Jupiter is above the horizon by a fair amount, and it does some radio emission, then I'm theoretically able to capture it with that device. Now I haven't, I installed it a year ago, over a year ago. Jupiter has never gotten above maybe 5 or 6 degrees above the horizon since then. But now, because of the way the orbits are tilted slightly, Jupiter is now rising with respect to Earth. And so next year, about this time, I should be doing pretty well with Jupiter radio emissions. That's pretty much what I've got going up there right as I speak. And there's the power supply. I use switch mode power supplies with lots of input and output filters. You can see an input filter here. You can see output filters here. These are pi type LC filters that I've got on the outputs of all of the power supplies. The Callisto is an instrument that's been deployed around the world. I actually build and sell these. I sell pretty much for everywhere and ship to everywhere in the world. And they have a native frequency range of 45 to 870 megahertz, bandwidth of 300 kilohertz, integration time of 1 millisecond. And I can monitor, I usually have it set up for 200 channels within this frequency range. And if I want to use it for lower frequencies below the native frequency range, then I have a series of up converters that I build for that purpose. And I'm working on some right now that go from 5 to 85 megahertz, specifically for the Callisto project. So those up converters extend the time and or extend the frequency range of the Callisto network down to some lower frequencies where the sun is really active. Here's a picture of the Callisto instrument itself. This is the instrument here, and then here's the up converter at HAARP. that I have. And you can see you come in through the back here from the antenna, go through a bias T into the splitter, and then you come out of the splitter here and around, and then pipe in to the up converter and then to the Callisto. So it's kind of a circular chain of RF to get in and then to the actual instrument that's doing the studies. There's another view of the bias T. There's actually two bias Ts here. One's for a future antenna preamp, and then an active one. Here's the splitter. Everything's connectorized. I have patch panels so that I can connect everything together and alter the connections if I need to. Here's an aerial view of the TCI 540 antenna. Its native frequency range is 3 to 30 megahertz. And this is another drone video. This is one that I took back in, I think it was August of 2019. So this is just a fly over from, we're basically west of the main transmitter. Here's the IRI. Here's the operations center. Here's the TCI 540 antenna here. And then here's my enclosure right here. So you can see that there's, it's heavily wooded area and tundra, and there's these cleared places where we've got the instruments and the antennas located. Okay. Here's just another view. Here's the TCI 540 antenna. Here in the background, you can see the 4 towers, 100 feet tall. They all converge in the center here. And then the coax run comes through the woods here and along, and it's ground laid in plastic pipe to keep the animals from chewing it up, and into the enclosure right here. Now, this antenna had nothing to do with the original HAARP facility. This was a Department of Defense antenna, and nobody knows really why they put it up there. But they built it and then took it down, stored it, and then built it up again. And what they were doing with it, nobody really knows outside of the DoD. They had 2 nice buildings right here at one time. And when the Air Force shut down, the DoD had this demolished. Now, it's my impression that what the DoD was actually doing here was going on hunting trips. So they would come up to interior Alaska on a taxpayer's dime, ostensibly to be doing some kind of a research project using their antennas, and they had a suite of receivers, as I understand it. But they spent most of their time on 4-wheelers and ATVs hunting and fishing in the area. So that's your taxpayers' money at work for you. Now, my plan is to replace that TCI 540 with an LWA antenna. The TCI antenna has a limited frequency range. It's a single horizontally polarized antenna, whereas the LWA antenna is a active cross dipole. It operates over a much wider frequency range. It has a pretty decent noise figure for that frequency band, and it has some gain to it. And it's only 1.5 meters high. So it's an antenna that is easy to maintain. It's ground mounted. It has a 3 meter by 3 meter ground screen below it to stabilize its pattern on different types of soils. And so I'll still have an SDR connected to the TCI 540, but all my main observations are going to be switched over to the LWA antenna. So that will hopefully be later this winter when I'll get that done. Here's a picture of the LWA antenna. It's about 5 feet from ground up to about this level right here. It's got each dipole is a sloped blade type antenna, and there's 2 of them at 90 degrees to each other. This picture I took in New Mexico at the long wavelength array installation outside of Socorro, and but my antennas are identical to this. And I also sell the LWA antenna. I ship them all over the world. I've shipped a couple of hundred of those things around the world. Now, I want to talk a little bit more about the Radio Jove project, because that's a citizen science project that has been going on for almost, I think, 20 years now. And it consists of a dual dipole, a receiver. We have a calibrator here so that the actual, emissions from Jupiter that we receive, we can actually calibrate them. And power supply down here. It's all hooked into the internet so that people can actually log into this receiver, or the software that is used with the receiver, and get a real-time trace of any Jupiter emissions that might be going on there. Here's a picture of the dual dipole. Here's one dipole over here, and then on the right-hand side, another dipole here. And when we built this, we used stuff that we found on the site to do it. These concrete barriers are holding up the aluminum mass. I don't think I put one single penny into this, because we found enough material on site to build these antennas and get everything hooked up. So we have the 2 dipoles. They come down, they go into this weatherproof box here, and inside that box is a phasing cable and a combiner. And so these are phased dipoles, and then we go back to the enclosure. Here's just another schematic of the dipoles themselves, and you can see that they're pretty simple. There's nothing fancy about them. They're about 20 feet off the ground, and the coaxes come down into a combiner, and one of the legs, the south dipole, has a delay line in it, or a phasing cable, to give a little bit of gain in the southern direction toward where Jupiter is going to be coming up. The patterns for the antenna, you can see there's a pretty large back lobe here, which is undesirable but unavoidable with such a cheap and simple type antenna. That's the receiver, the Radio Jove receiver. I think these are about a couple $100, and when you buy the receiver, you actually get the antennas with them. They give you all the wire that you need, all the coax, everything you need to put this together and actually put up a working system. It's a direct conversion analog receiver. It's a fixed tune, 20 megahertz or so, but it has a slight or a small tuning range associated with it, so that you can tune out or tune off of any interference. It's got a 3.5 kilohertz output bandwidth after the detector goes into a PC sound card, and then the actual data is derived using radio SkyPipe software. And maybe some of you have heard of radio SkyPipe and maybe use it. And it's a super reliable software program that can be used with the Radio Jove to actually get your data into a digital format so that you can plot it and so on. What the Jupiter radio emissions, we talk about Jupiter having radio sources on it. It doesn't actually have a fixed a place on the surface because it doesn't have a surface. But this moon right here, the volcanic moon Io, as it rotates around Jupiter, there's a cloud of charged particles that surround it. And those charged particles interact with Jupiter's magnetic field to produce really, really strong radio emissions. And this is what it looks like schematically, but I've got a movie here or an animation that shows what is going on. You have to kind of look at this for a minute to figure out what's happening, but you can see Io is this red dot orbiting Jupiter. Jupiter is rotating, and when this moon is in a certain position with respect to Jupiter, it sends out transmissions. And when those transmissions are pointed toward Earth, then we receive them. So these transmissions are actually, or the emissions are actually happening all the time, but we only receive them when this beam is actually pointed toward Earth. And I'm going to back up here and play some of the emissions that we can hear from Jupiter. And this is called L bursts for long bursts. It sounds like just an increase in radio noise, but this is what it actually sounds like when you have a receiver tuned in the neighborhood of 20 megahertz and you're receiving receiving Jupiter. Yeah, that's the wrong one. There we go. Can everybody hear that okay?
Yep, we hear it.
It just sounds like static, doesn't it?
Right.
Let me shut off these other ones here.
With a little bit of a siren effect.
Yeah, that's because one of the playbacks here is gone berserk on me. What you heard was what sounded like just ordinary static, didn't it? But after you've had some practice with Jupiter, these emissions are more or less predictable. So you can listen at the predicted time, and if you hear an increase in noise that sounds like that, then, whoops, I keep hitting the wrong button here.
Also sounds like ocean waves.
Yeah, I was going to say, it sounds like the surf coming in and out.
Okay, so those are L bursts and for long bursts. And that is one type of emission. We also can hear, now, hear that popcorn? those are also Jupiter emissions. They're called S-bursts. Sounds like popcorn popping or somebody throwing rocks up on a tin roof or something like that.
But they're reflections, or are they originating?
What was that?
Are they reflections of radio
No, they're
waves?
not
Or
reflections. They're actual emissions. And they just sound that way when detected by a narrowband receiver. So I thought I had a slow speed version. Yeah, I do. Oh, no. For some reason, I can't get the slow speed version to work. I must have goofed it up when I loaded it on here. But you can do this from the comfort of your own home. This is what's so great about the Radio Jove project, is that it's something that if you have a reasonably quiet, if you live in a reasonably quiet area, you can put up your dipoles and hook up a receiver. You don't need to use the Radio Jove receiver that I showed. There, you don't have to use that receiver. You could use any receiver that's tunable to about 20 megahertz or so. Now, these radio emissions actually cover a much wider range, but because of Earth's ionosphere, chances are you're not going to receive much below 15 megahertz. And the upper range for these emissions, because of for technical reasons, is about 43 megahertz. So you have a pretty wide band in there that, and people that do this regularly are able to receive from about 15 to 16 megahertz all the way up to about 30 megahertz on a regular basis when Jupiter is within view. So this is kind of a fun project. And if anybody's interested in this, I can give you some places to go. Okay, so that's pretty much about the Jupiter project. There's a lot of things that go into play if you're trying to do this, but there are software programs out there where you can that will help you predict when Jupiter is going to be active, and so you can listen or record only during those particular times. So I mentioned that I haven't been successful doing any Jupiter observations from my HAARP facility. And okay, so what have I been doing meanwhile? Well, meanwhile, I've been doing galactic background radiation observations. And that's where I'm just basically receiving the cosmic radio background, also called sky noise, and recording that and just watching, seeing what's going on. This plot that you see here is a 24-hour plot of the cosmic background radiation. It's also called synchrotron radiation. And you can see that it rises to a peak in this case at about 0600 coordinated universal time. Everything is in UTC. So in this case, it rose about 3 dB, maybe 2.5 dB throughout the 24-hour period. And so it's kind of fun to watch this type of radiation. It's coming from the Milky Way. And because it is linked to the Milky Way, that means that every day it's going to come it's going to peak about 4 minutes earlier than it did the day before. That's about 2 hours each month. So if you do this over a long period of time, you can watch this peak migrate to the left over time. And I think I have a, whoops. Here's the peak here. And you can see it's migrating to the left. And that's the cosmic background radiation. And the reason it jumps around so much is because I started having trouble with the, you can see that the plots got, they're really jagged. And I started having problems with that, and I haven't totally resolved that. On my next trip I will. But you can see that the cosmic background radiation is migrating. It works out to be almost exactly 4 minutes a day, earlier each day. And so over a month or over a year's period, you'll see this thing migrate over the full 24-hour period. So that's what I've been doing with the Radio Jove receiver for the last year or so, is making these types of observations. Now, next year, the Jupiter itself will be quite a bit higher above the horizon, and hopefully I'm going to be able to do Jupiter emissions as well. Now, there's nothing I can do to stop this cosmic background radiation, but I'll be able to, since the Jupiter emissions are over a short period of time, then all I have to do is home in on a particular part of the recording to see them. Okay, well, that's pretty much what I've got. Here's some web links and references. You can go to the HAARP homepage. If you're interested in the actual science that's been done, they have, there's a list of all the publications associated with the HAARP research over the last, since the 90s. And if you're interested in anything that has to do with radio astronomy or radio science, I have a whole bunch of stuff on my website that you can take a look at too. So if you have any questions, let me know. I'll try to answer them. And what I'm going to do as a parting shot here, I'm going to show you one of the things that we have to contend with at our remote sites. And this is actually right outside my window here in Anchorage. This was about 11 o'clock at night. Those guys wander through my yard pretty regularly. I have to carry a shotgun when I mow my lawn. Okay, so I'm going to stop sharing. Does anybody have any questions?
Yeah, well, I've got a silly one.
Go.
Why are the amateur calls for Region 2 when they're clearly not in the East Coast of the United States?
What are the, say that again?
They're amateur calls, WI2XFX, and that's a Region 2, which is East Coast. I'm wondering why they got those calls.
I can't answer that. That's what was assigned to them, probably having something to do with the Air Force way back when. And so, yeah, I don't know why they're out of region.
I have a question. WS2N, Paul.
Go.
Oh, okay. I found an article in QST. This is 1996, And page 35, they had a couple of pages on this topic. And one of the things that they were wondering about at the time, it wasn't fully active. They were just going to run like a half a dozen antennas. And then if that worked out, then they were going to do more. But they said here that they were going to wait for a magnetic field to pull the cloud away from the area. And then the cloud might go either east or west. And different hammers might be able to transmit and bounce their VHF signals off of, or UHF, off that cloud. And I wonder if that ever came about, because it's 1996. Did they ever do it?
I think that there was some experiments that were that did try to do that. In fact, there was one in I think it was early 2019, where they tried to specifically do that, where they had UHF, these were radio amateurs in Anchorage and Fairbanks. This would be north and south of HAARP. And they burned up the ionosphere above HAARP and then tried to do the communication. And I haven't seen any report come out of that. It was a kind of a half citizen science, half science project, but as far as I know, it wasn't 100% successful. So people have tried to do exactly that, but I don't know if they've been really successful at it.
Okay, very good. Thank you.
Whitham, what would you say is the most significant discovery made over this period of time?
You know, I have only been involved with the HAARP since 2016 or so. I don't really know what significant things they have done. I don't think that there's been earth-shaking discoveries. What they have done, though, is added to our knowledge of the magnetosphere, the ionosphere, and things like that. So it's been kind of, I look at it as kind of an incremental thing, where they've maybe answered a question or two or three, but nothing. I don't think their goal was ever to discover anything. It was to answer technical questions.
Okay, and as far as you know, they never were involved in any type of UFO detection or
mind control, or no. As far as I know, they were not.
Because you said it was under the Air Force originally, so I just wondered if they had ever been asked to collaborate with any of the efforts.
There are certainly conspiracy gadflies that are convinced that everything the Air Force did was to for whatever. And so as far as the UFO thing and mind control, earthquakes, and all that stuff, that's pretty well been all debunked, I think.
Oh, too bad. Okay.
Sorry.
Anyone else have any other questions for Whitham?
John.
Sure.
Oh, go ahead,
George.
John first, then George.
Just a quickie. I always got the impression that most of the HAARP research had to do with ionospheric modification for basically military communication during military activity and how to set this up. I do remember there was one, it was a large project, the ELF project involving through Earth communication to submarines. So all of it, to me, seemed like it was always involved with minor and major ionospheric modification for increased emergency communication. Am I right on that? It seems like
No, I don't know if that was the focus that the Air Force had. I know that all of the research that I have seen and is publicly available, I've never seen anything about that particular subject. You can look at that online list of publications and maybe you'll spot something in there. You know, the researchers are really good about giving a name to something that doesn't make sense. So you might spot something in those research papers that'll trigger maybe something in your mind that, oh yeah, maybe this is worth looking into. So good luck with that though. But those papers are all, there's, as far as I know, none of the papers that are publicly available were ever classified. Now, I'm not saying that the Air Force didn't do classified research. I mean, I'd be surprised if they did not do any classified research. But of course, we're never going to know about that because we'll never see those papers.
And George?
Am I coming in?
Yeah.
Okay, thank you. I'm very interested in getting a PDF copy of the presentation. And I could tell you that there were efforts that were coordinated with laboratories in northern New Jersey. That's maybe where the WI2 call came from. I can research that, but I would like to get copies of the presentation along with contact with our presenter because there is some information that I may be able to help him with. It was actually stemming from the early 1970s in efforts to gain some military control. And at the same time, during the end of the Reagan administration, funds were provided for efforts like this. Aware of it, and I would like the copy of the presentation and the presenter's contact.
Well, I can get that to you, George.
Yeah, Harry can give you my contact information, and what I'll do is over the next day or so, I'll make a PDF copy of the presentation and I'll send it to Harry. And then Harry, could you just be my point of contact
Sure.
for that and disseminate it to anybody that's interested?
No problem. Maybe we'll
Yeah.
put it on the website and make it generally available, if that's okay.
That'd be great. And that way you don't have to, nobody has to worry about what my contact info is, although it's in the presentation.
Oh, thank you. Harry will be in contact, KD2FIU clear.
Okay.
Okay. Does anyone else have any other questions for Whit?
Lou has his hand raised.
Okay, Lou, go ahead.
Yeah, you mentioned, I'm blanking out on names of organizations you mentioned earlier, but at school, we set up a project a couple of years ago, which has been suspended because of physical location issues at the school, that we were monitoring one of the very low frequency transmitters in the 20 kilohertz range, and using that, feeding that into a sound card and using that to detect solar activity affecting the ionosphere. And I think you may be familiar with that. I wonder how all of this ties in. And of course, those very low frequency transmitters are used for submarine communications that John was referring to.
Right. Yeah, you're referring to the sudden ionospheric disturbances, or SID. when you have a solar flare, it alters the height of the D region, which in turn alters the propagation of the VLF transmissions from these huge transmitters. And I do a lot of that myself. In fact, my Coho observatory, about half of that observatory is dedicated to that purpose. I have 2 loop antennas for it. But as far as connection to the HAARP, I don't know of a direct connection, because when the HAARP transmitter is heating the ionosphere, it's only doing heating a small patch of ionosphere above. We're talking maybe 15 kilometers across or so. And so a VLF transmission that's being guided by the Earth ionosphere waveguide, that's just going to be a pebble in the highway on its way to wherever it's going. So I don't think that the HAARP itself would affect any of that. And I could be wrong, but I think that that's a totally different, kind of a totally different project.
I just thought it was interesting how they sort of overlap in the technology anyway.
Right.
Okay, any other questions from anybody? I will take the silence to mean no. I'd like to thank you, Whitham, for, from my perspective, an extremely interesting presentation. And maybe we can have you back again sometime for some sort of follow-up presentation.
Yeah, thanks, Harry. I'm glad to do that. And yes, if you have anything in the future, just let me know and I'll see what I can do.
Thank you very much.
You're welcome.